Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about step-by-step design procedure for two-way unrestrained slabs. So let us see the outcomes of today's class. After completion of this class, we will be able to know what are the steps for designing unrestraining slabs. So you know what is the unrestrained slab means? This is also called as a corners of a slab are not held down. They are free to lift up the slab. So there is no provision of any torsional reinforcement over the edges of the slab. Those slabs are called unrestrained slabs. So let us recall the things what we discussed in previous class. In previous class, we have discussed about a complete design of two-way restrained slabs. You know the restrained slab means the corners of a slabs are held down, means they are prevented lifting of their corners by providing some brick wall over that or any another floor construction of another floor over that or slab and your beam casted monolithically. By means of this two of fixity, we can make our slab restrained. So for these slabs, we have to provide a torsional reinforcement. If we are not allowing the slab corners to freely lift, then there may be a chance of occurring whatever torsional stresses are occurs. Due to those torsional stresses, there may be a chance of occurring cracks in that. In order to arrest that crack, we have to provide a torsional reinforcement along the corners of the slab. And this provision of a torsional reinforcement is majorly depends upon the edge condition of the slab. If the slab is resting over four discontinuous edges, then we have to provide all four sides the torsional reinforcement. If it is a continuous over one edge and discontinuous another edge, I have to provide where these two discontinuous I have to provide there the reinforcement where the two discontinuous edges of slab meeting at a point, there also we have to provide a torsional reinforcement. If when we have the two discontinuous edges of two continuous edges of slab, there is no need of providing torsional reinforcement. And we have completed design by taking one problem how the two-way restrained slab will be. So what are the steps we have followed for there? There we have followed first we have to calculate assumed effective depth. You know how to calculate assumed depth for slab by using codal provisions, that is Lx by d ratio, that is depends upon the Lx length, span length and live load of the live load which is likely to come on the slab. Then we have to calculate effective length. For effective length calculation, we have a codal recommendation. We have two criteria. Minimum of that two criteria value will be taken as a effective length of the slab. Then based on the effective length calculated, we have to, the third step would be calculation of total load. The total load means the total dead loads, live loads, or any floor finishes are there. Those loads also consider. So total load must be equal to dead load plus live load plus any finishes. And for design purpose, we have to enhance our actual load which is likely to come on the slab by partial factor of safety 1.5. That is 1.5 into total load will give me the design load. Right, after calculate design load, we have to calculate minimum effective depth required. Before that, we have to calculate what is the maximum bending moment occurs this. So this bending moment can be calculated based on codal provisions. Say if we want to calculate here, as we are designing two-way slabs, in two-way slabs we have to calculate the bending moment along the x direction and y direction. Along the x direction, we have to calculate mu x equal to alpha x w lx square. That is alpha x is the bending moment coefficient along the x direction, and this also depends upon the edge condition of the slab. Similarly, MUY we have to calculate. It is a bending moment along the y direction. It is alpha y mu lx square. Right. And this alpha y is the bending moment coefficient along the y direction. So based on these two formulas, we can calculate the bending moment along the x and y directions. Then we have to calculate for given bending moment and given load, what will be the minimum effect of depth required for this particular slab. In this case, we have to equate our maximum bending moment is equal to the limiting bending moment. Then we'll get one formula that is small d equal to under root of mu by k into bd. That is k is that that depend upon the your grade of steel. Here the question is, what is the mu here? Mu means the maximum bending moment value which will be provided here in this formula is maximum of bending moment occur along the x direction, along the y direction. That value will be provided as a your what mu value. From that we have to calculate d, that is called a minimum effective depth required. That minimum effective depth required must be less than our assumed depth. Then if it is so, then we go for further step with our assumed depth. If not, then we'll modify the section. Like that we can calculate effective depth. And similarly we have to calculate area of steel along the x direction, y direction. As you know that we have divided our two-way slab into middle strip, edge strip along the x and y direction. In those areas we have to calculate the reinforcement. And similarly here we have another provision of reinforcement. As our slab is restrained slab, we have to provide the reinforcement in corners also. That is called a torsional reinforcement we have to provide. Those torsional reinforcement are provided based on the codal provision at the corners of the slab in order to prevent the occurring of cracking. So there is a provision based on that we have calculated. Then we go for checks like deflection check, development check, and shear checks. So based on these are things we have designed our two-way restrained slab. So let us start our today's discussion on unrestrained slab, design steps for unrestrained slabs. So you know that unrestrained, what is the definition of unrestrained slab is? Unrestrained slab means what? A slab which the corners are not prevented lifting from the lifting are called unrestrained slabs. So these are the unrestrained slab. Here generally in the restrained slabs the corners are lifting up. In the case of unrestrained slab, corners are not lifting off. So that's why it is called a unrestrained slab. So here when the slabs are simply supported on the walls and neither parapet wall nor upper floor walls are constructed to the corners of slab free to lift, not held down, and known as a walls are coming. See, the meaning of this statement is how here it is corners of this are preventing not preventing from lifting, means we are not constructing slab and beam as a monolithic. Moreover, we are not constructing any parapet wall over the slab. That's why we can call this slab as a unrestrained slab, or the slab with corners are not lifting of slabs. Right? Now we'll see what are the design steps for this designing unrestrained slabs. So the first step would be similar. The steps are similar to your design of restrained slab, but only thing is the steps will be changed. Where we have to provide torsion reinforcement. Here we will not provide a torsion reinforcement. Another thing is when we are calculating your bending moment coefficients, the table what we are used here is different from table what we are used there. So that is the only difference here. So let us see how to calculate effective depth of the slab. Right, this is based on the stiffness criteria given in code IS 456-2000. Right, codal provisions, based on the codal provisions we have to design. Right, next what is the codal provision? So to calculate the LX by D ratio, here it has to satisfy this condition. Then we'll use these values. What are those values? Say if your LX is less than 3.5 meters and live load is less than 3 kN per meter square. If we are designing a simply supported slab, then and for moreover if you using a grade of steel is Fe250, then we have to use Lx by D ratio is 35, and whereas if you are using Fe415, then we can use 28. Or if you are designing fixed or continuous slabs, then for using Fe250, then your Lx by D ratio is 40, and for Fe415 your ratio is 32. Similarly we can use, and for this particular case when your Lx is less than 3.5 meters and live load is less than 3 kN per meter square, then we have to use these conditions. If the case is different, the another case is what? If your Lx the shorter direction length is 3.5 meters and live load is greater than 3 kilonewton per meter, then we can use L by D ratio, Lx by D ratio, same as how you use it for your one-way slab. That is what are the values I used for one-way slab? If you remember, the Lx by D ratio can be calculated for simply supported slab is 20. That value will be vary from 25 to 30. Between those two values, we have to choose our Lx by D ratio value, and we have to calculate the effective depth. How to calculate effective depth here? We know that Lx here L by D, and that equal to some value, say 28 I am assuming, say. From this I want to know what is the D is. Here from this I can write D equal to, that is L by 28. Here L is your what? Lx, I can say Lx is the shutter span direction, and x is that basic value. If I divided the span by basic value, we get what is the effective depth is. Like that, we can calculate effective depth of the slab. For this case, when our Lx is less than 3.5 meters and live load is less than 3 kilonewton per meter square. So if the case is this reverse case, then we have to choose, as similar case of your one-way slab, that is Lx by D ratio can be chosen between 25 to 30 value. So among this value we can choose and finally calculate what is the L or D value is. Right. Next step. The next step would be effective span. You know how to calculate effective span? As we are designing simply supported slab, then as per IS 456-2000, there are two recommendations, the two criteria are given. Criteria 1 is a clear span plus effective depth, and criteria 2 is center to center distance between the support. The minimum of these two values, the least of these two values will be considered as your effective depth. This can be calculated in x direction as well as in y direction. So what do you mean by this? So you suppose if you take a simply supported beam here, and this is a simply supported beam, roughly I am drawing, please. This is a beam which is simply supported here, right? And this is a clear span. The clear span nothing but a distance between inner face of the support to the inner face of the support, and this is what your width of a support. In both the cases we have same width, and this is a beam, simply supported beam, I can assume it, and the effective depth of this beam is a small d, right? So with respect to first place, what is that? Clear span plus effective depth. Clear span means this small L I am representing, it is the length distance between the inner face of the two supports. So this is L, and plus the effective depth of slab is this small d is one condition, and one more condition is the clear distance between supports, that is center to center distance between the support, not clear distance, and is the center of support is this. So this is one center of support, and this is another center of support. This distance is the one more condition. This how can we calculate? So this can be noted that, so your small l plus half the width in one support, that is W by 2. I am assuming here width equal to W. Please don't consider as a load or force. And one more is this right hand support is W by 2. This is how we calculate the effective span in x direction as well as y direction. The minimum of these two value will be considered as a effective length along the x or along the y. If you are calculating effective depth along the effective length along the x direction, here you have to, in clear span, you have to substitute along the clear span Lx value, x directional value, and if you are calculating along the effective span along the y direction, in place of this L you have to substitute what is the length of the slab along the y direction. So after substituting that, we will get that effective length of the span. Then load calculations. I already told you that on any structure we have come across three types of load basically. One is a dead load, a live load, and then floor finishes. Right? And this dead load nothing but a self weight of the any member. As we are designing a slab for 1 meter width of this, so the dead load of slab can be calculated by using this formula. What is that? It is a overall depth, I can say OD, overall depth, and this is 1 meter width, and this is 1 meter length, and this is 25 is, as we are designing a slab, a RCC slab, so the unit weight of RCC is, what is that? 25 kilonewton per meter cube. So if we calculate all together, we'll get the value final, the dead load in terms of a kilonewton per meter. Similarly, we have a live load in terms of kilonewton per meter, a finishing load in terms of kilonewton per meter. Then we have to calculate the total load. What is the W is? I told you the sum of all the loads, that is the dead load, live load, and 4 finishes. So after calculating total load, you have to enhance this total load by using some partial factor of safety, so that we can calculate what is the factor load is. Generally the factor load is designated with a W, and the partial factor of safety used for a limit state of collapse in flexure condition is 1.5. So the total load will be multiplied with this 1.5, then we will get what is the factor load is. Right. After calculating factor load, we have to calculate the bending moments. So as I already told you, the bending moment is mx equal to alpha x w lx square. It is bending moment along the x direction of a slab. You know, the slab will be like this. So slab is, I am drawing a plan. So this is shorter direction, so I can call it as a Lx, and it is a longer direction, I can call it as a Ly. Right. So we have to calculate the bending moment value along the shorter direction, right, and then we have to calculate the bending moment value along the longer direction also, because as we are designing a two-way slab, our slab will bend in both the direction. What is the amount of bending moment likely to come on x direction, and what is the amount of bending moment likely to come on y direction? Those values we have to calculate. So how to calculate those values? Mx equal to alpha x w lx square. Here you know the alpha x and alpha y are the bending moment coefficient along the x and y direction, and w is the total design load or factor load what we are consider now, and lx is what is the shorter span direction is, that is the effective length of shorter direction. If you substitute those values, we can calculate what is the mx and my. So these alpha x and alpha y values are depends upon edge conditions, right? If your slab is resting over a simply supported and all edges of slabs are discontinuous, say like this, I am designated with I am showing here with a some hatching lines to make it discontinuous, right? So if we draw the bending moment diagram in this direction, we'll get a bending moment along the this direction is like this. So here we have only positive bending moment along the midspan, because there is no continuous in this direction, in this direction, or in this direction. And similarly, if we draw the bending moment diagram along the y direction, here we get the bending moment diagram like this. Sorry, it is somewhat like this. And this edge also discontinuous along this direction, in this direction. So we'll get the positive bending moment at the midspan. So we'll get here the positive bending moment, here the positive bending moment. So moment of coefficient occur also a positive moment of coefficient. So that values are dependent of, that may be positive or negative, that is based on the your what type of bending moment is likely to occur. So that's how we calculate mx. Then we go for coefficient of bending moment. Unlike when we are designing a torsion restrained slabs, then we are used a table number called 26 for calculating bending moment coefficients according to IS 456-2000. But here for calculating bending moment coefficients, we are using table number 27 of IS 456-2000, and these coefficient values are depend upon the Ly by Lx ratio. For different Ly by Lx ratio, here we have 1, 2 up to 3, and these are the alpha x and alpha y values. So based on that, based on the Ly by Lx ratio, we have to calculate what is alpha x and alpha y. After knowing the alpha x and alpha y, we have to calculate what is the bending moment values are in the x direction and y direction. So for example, if you obtain your Ly by Lx value is say 1.1, then alpha x corresponding to this is this and alpha y corresponding to this is this value, right? So dear student, remember that according to IS 456 table number 26 is used for designing or the calculating bending moment coefficient for restrained slabs, and whereas the table number 27 is used for calculating bending moment coefficients for unrestrained slabs. So here the example I will explain you. In case if your Ly by Lx value is falls between your 1.2 and 1.1 and 1.2, say that is 1.14, then how to calculate this alpha x and this alpha y? So by using interpolation technique, we can calculate what is alpha x and alpha y value. Then after knowing that alpha x and alpha y exact values, we can calculate mx and my. So this is how we identify or calculate the alpha x and alpha y value from the table number 27 of IS 456 2000. So we will proceed to next step. Next we have to check for effective length of the, what is that, effective depth of the slab. So that is called a minimum effective depth. For calculating this, we have to equate our maximum bending moment to the moment of resistance. That is the moment of resistance of a member. So what is the maximum bending moment? Generally, when we are deciding our designing our beams, we have used mu, limiting moment of resistance mu limit. And here in the slab, as we are designing two-way slab, we have two different bending moment values, among which value will be used as a mu here. Among mx and my, whichever is the greater, that value will be used as a mu here. So corresponding that maximum value of bending moment, we will calculate what is the minimum effective depth required. So assume that this is m maximum. So maximum moment of maximum factored bending moment we have to substitute here among mx and my, and you know that mu limit equal to k into fck bd square, and this k value will be depends upon grade of steel. For Fe415 it is 0.418, for Fe250 it is 0.4 or 0.148, and Fe415 it is 0.138, and for Fe500 it is 0.133. So based on the grade we can substitute what the k value is, and FCK is grade of concrete. You know, B is we are designing the slab for 1 meter width, so it is 1000 mm will consider generally, and D is equal to effective depth what you are already assumed depth. And after substituting all those values, we'll get this small d equal to under root of mu by k into FCK, and k value substitute and FCK value given as a grade of concrete, and B is 1 meter width of the slab. And you know, I am repeating here, mu is maximum value of bending moment along the x and y direction that were provided. Suppose if your D required, minimum depth required is less than assumed depth, that is what we are assuming in first step, then it is okay. If not, if your D required is greater than assumed depth, then we have to revise the depth and follow the above procedure. So this is the thing you have to calculate, you have to check in effective depth with respect to minimum effective depth required for given bending moment, that you have to check. Next we have to calculate the area of steel at a midspan. As I already told you, our slab will be divided into a edge strip. Say this is a slab, this slab will be divided, so this is a y direction and this is a x direction, shorter direction. This slab will be divided along this y direction into 3, that is, so it is a edge strip and it is a middle strip and it is also edge strip. So and along the x direction also it is divided, there is a edge strip and is a edge strip and this is a middle strip. Like that we have to divide our slab, two-way slab. So in these regions we need to calculate what is the area of reinforcement to be provided. Say by area of reinforcement provided, we can calculate by using these two formulas. So for what is our step? How to calculate area of steel at the midspan. So midspan means along the x direction we have midspan, along the y direction we have a midspan. So if you have to calculate area of steel in midspan region, then we have to use this formula, that is MUX is equal 0.87 Fy ASTX T into 1 minus Fy. This is, it is not a 1 minus here, generally this is 1 minus to this whole term, 1 minus Fy ASTX by FCK into BD. So from this we have ASTX value we can calculate. If you substitute the Fy value, D value and FCK value and B value, you will get a quadratic equation. If you solve that quadratic equation, we will get what is that ASTX is. What is meaning by ASTX is area of steel in middle strip region of X direction slab, that is shorter direction of slab. Similarly, we can calculate what is the area of steel provided in middle strip region of Y direction. So that is MUY is equal to 0.87 Fy ASTY, and is a D dash is the effective depth along the Y direction, whole multiplied by 1 minus Fy ASTY by FCK into BD. Here also we will get a quadratic equation. If we solve that quadratic equation, we can calculate what is the ASTY is, right. So next step would be, after so with this our design is over, I think. So we have assumed design means calculation of dimensions. So we have calculated B. We are assuming that B is 1 meter width, and effective depth we have calculated and we have checked it also. Then we have to provide area of steel. So these three parameters nothing but a design. But design means knowing the cross section dimensions and area of steel in the RC elements. Those things we have calculated now, right? Then as you know that MUX correspond MUX that factored some terms here what you used in this step-by-step design procedure. So MUX is factored bending moment along the X direction, MU is the factored bending moment along Y direction, and Fy is the yield strength of the steel, FCK is the characteristic compressive strength of steel, and ASTX is what area of steel in mid strip region along the X direction, ASTY is the area of steel provided in middle strip region along the Y direction, and small d is effective depth of the slab in X direction, small d dash is effective depth of the slab in Y direction, and B is what is that width of the slab, generally taken it as a 1 meter. These are terms what you are likely to use in this step-by-step design procedure of two-way unrestrained slabs. Right, how to calculate the effective depth? As I already told you that the effective depth will be different from X direction to Y direction. So if you want to calculate what is the effective depth along the X direction and what is the effective depth along the Y direction. So is section, if I draw here, say this is a slab cross section, it will show the overall depth, right? This is a overall depth, and here we are providing a reinforcement, right? This will give me a cover, say a clear cover. Clear cover means the distance between bottom of the slab to the bottom of the steel reinforcement, right? And here say it will enlarge the reinforcement bars here, please excuse me, and this is the half of diameter. So if you have to calculate the effective depth of the slab, that is small d is equal to, what is that, overall depth minus clear cover we have to deduct, and half of the diameter will be deducted. Then we will calculate, then we know what is the effective depth along the X direction is. So it is easy to calculate in Y direction, that is d dash, that is effective depth in X direction minus what is the diameter of bar we have choose by half of the diameter will give. So it is not half, the full diameter, sorry, it is this and this cut d minus phi, that is effective depth along the X direction minus one full diameter of the bar, that will give the effective depth along the Y direction. So here already we have discussed small d is effective depth along the shorter direction, effective depth along the shorter direction. D dash is effective depth along the longer direction. So capital D is overall depth. Phi dash diameter in the main bar. Phi is the diameter y direction. Generally, these two are same. Here you can use the diameter of bar this along the x direction and along the y direction are same. Right. Requirement is provided as follows. Reinforcement is provided as follows. See which reinforcement has to provide where. The steel bars along the span are provided bottom layers and steel bars along the long span provided above the shorter span. So if it is your shorter span direction is this and steel bars are provided first, shorter span main bars are provided below like this, and over that we have to provide our longer span reinforcement so that will effectively withstand the what is that maximum of the bending moment which is likely to occur. So generally the bottom reinforcement is shorter and the top reinforcement is a longer direction, right? So shorter direction main reinforcement will provide a bottom below, and above the shorter direction reinforcement longer direction reinforcement will be provided. And spacing to be maintained for this main bar should be, one is a 3D, another is 300 mm, whichever is less. So among these two values, whatever the value you have, minimum value, that will be provided as a spacing. But in general we have three cases here. Based on our obtained data, we will get one spacing that is actual spacing obtained, and we have according to IS 456-2000 we have condition 3D and 300 mm. We have to take minimum value of these three. What is that? Minimum value of these three will be considered as a spacing for main reinforcement along the x directional bars and y directional bars. Right, this is a spacing to provide, but we have to follow this. They should not be increased this more than these two values, that is 3D and 300 mm. Right, and now we have to calculate, as I already told you, that we have to calculate area in midspan region as well as in edge strip region. So how to calculate area of reinforcement in middle span, that is edge strip region. So in edge strip area of steel at edge strip region, here the code says, that is IS 456 says, the minimum area of reinforcement will be provided for edge strip. So what is the, according to code, what is the minimum area of reinforcement? If you are using a FE415, that is FISD bar, that is FE415, so cursor is not, FE415, that comes under category of HYSD bars, then we can use 0.12% of gross cross-section area of the beam, that is slab. And if you are using a mild steel nothing but what, that is your FE250 grade of steel. If you are using that mild steel, then we have to use minimum area of reinforcement is provided 0.15%. So based on the grade of steel, we can choose the percentage of steel to be provided as a edge strip reinforcement. Then we have to maintain the spacing also. For that also we have to maintain spacing. As per IS 456, spacing will be 5D is one condition, another is 450 mm, whichever is the minimum, that value will be provided. But along with these two, we have one more obtained value of spacing based on assumed diameter of bar, that we can calculate what is the spacing to be provided. A minimum of these three will be provided as a spacing for the edge strip reinforcement. So this is how we calculate area of steel in middle strip region and edge strip region along the x directions and y directions. So let us go for check. After designing all the values, we go for check for your two-way unrestrained slab. So how to do the check for this? Check will be based on, the first check is your check for control of deflection. So as usual, how we did for our restrained slab, same thing we have to do here. That if by check this, we should know what is the percentage of steel and what is that FS. What is FS means stress in steel under the service load. The percentage of steel can be calculated by using formula PT equal to 100 ASTX provided by BD. What is the 100 ASTX here? Area of steel provided along the midspan region of X direction of the slab. and B is 1 meter width, and effective depth is what we calculated, that will from the step 1 is that value have to substitute here. So after knowing the percentage of steel and then after knowing Fs can be calculated by using this formula. This formula is available in our IS 456 2000, that is Fs equal to 0.58 Fy AST required by AST provided, and this by using these two values we can calculate what is our KT. What is the KT? KT is the modification factor. This modification factor can be obtained from this graph which is available in our IS 456 2000. This modification factor values depends upon what? Here percentage of tension reinforcement and Fs value. Here we have a cause for Fs value. So if you are getting some say 4% of tension reinforcement and Fs is 240 Newton per mm square. Now this is a 4% and project this value of 4% onto the your curve straight, just go straight here, and here will intersect on the Fs value of 240, and this value will be projected onto the y axis. Whatever the value we get here, that value is the MF, the KT. KT is what? Modification factor. Say for 0.4%, if it that Fs equal to 240, so I am getting here is this value. It is intersecting on y axis here. So almost this value will be this 1.2, 1.4 and 1.6. It is somewhere 1.35. So I can designate it as KT value is 1.34, and that value will be multiplied with the basic value. You know, for simply supported slab, the basic value as per IS 456 2000 is 20. But 20 into that 1.35 will give me the L by D maximum, that L by D ratio maximum we can provide. But what is L by D provided? Already we have calculated effective length, and what already we have calculated azimuth depth. The ratio of these to these will effective length to that effective depth is provided, and the ratio of L by D maximum will be basic value into modification factor. Finally, if your slab set to be safe in controlling the deflection, then your L by D maximum must be greater than L by D provided. So this is how we check against the deflection of a slab. Then we go for check for shear. So maximum shear force at the edge of two-way slabs are given like this. First we have to calculate what is the VU axis. What is the factored shear force along the x direction. That value can be calculated VU by R power 4 by 1 plus R power 4. That R power 4 into whole multiplied Lx by D for simply supported slab. Here R is nothing but what? R is ratio of shorter span, longer span direction to the shorter span direction, that is Ly by Lx here. Like that we can calculate Vx. After knowing the Ux, we have to calculate what is the nominal shear stress is. You know the nominal shear stress. How to calculate nominal shear as per IS 456 2000 according to class number 40.1. We have the nominal shear stress value will be tau E equal to what is the VU by this is VU by BD. You know VU is VUX here, that is the maximum factored shear force along the X direction. That value I can consider, and B is 1 meter width of the slab and D is effective width of the slab. So the effective depth of the slab, if you substitute those values, we will get what is the nominal shear stress is. After knowing the nominal shear stress, we have to calculate what is the design shear strength is. Design shear strength of the concrete, that is tau C. So this value depends upon percentage of steel and grade of concrete. If the percentage of steel is 0.25 and grade of steel is M15, then we can consider that your tau C value is here this 0.35. Like that we can calculate. This value will be available in IS table number 19 of IS 456. So this the table I have copied here. The table I have copied here, that is table number 19 of IS 456. With the help of this we can calculate what is the tau C value is. Right, after knowing the tau C value, as per for the slab, to satisfy the shear condition, our nominal shear stress must be less than or equal to what? K times tau C. Here K is a one value, factor value, that is depends upon the overall depth of the slab. According to the class number 40.2.1.1, we have a K values like that. If the overall depth of the slab is 300 meter, then 300 mm, then the K value is 1. For say like this 275, 250, 225, 200, and 275 finally. If the overall depth of slab is 150 or less, then we can use K value as 1.3. So that the obtained tau c value will be multiplied with the K, and then we have to compare our K into tau c will be the actual shear strength of a slab, flat slab. Then those value can be compared to tau c. If our tau v is less than K into tau c, we can say our slab is safe against the shear. Then you have to check for development length now. So LD can be calculated by less than or equal to M1 by V. M1 is the LD is development length of the bar. M1 is the bending moment at the section consider. V is the shear force at the section consider. L0 is the anchorage length. LD can be calculated by using this formula, that is 0.87 F55 by 4 into tau BD. Right. If the obtained value of LD is less than this factor, then we can say our slab is safe against the development length. So what we discussed today, we have discussed the design steps. Let me summarize the step. First we have calculated, assumed the depth, then effective depth we have calculated. After that total load. By total load we are enhancing by factor of by multiplying partial factor of safety. Now we have a factor load. After knowing the factor load, we have calculated bending moments by knowing the coefficient of bending moments from table number 27 of IS 456-2000. Then we have calculated area of steel in middle strip region, edge strip region, along the x direction, y direction. Then we have checked against deflection, shear and development length. So thank you. That's all for today's lecture.